My name is Amir. I'll be presenting pose-conditioned image generation, which is work done in collaboration with Shabam. So in this work, we are interested in exploring ways of generating images of a desired car model and background. We also want to condition on a target pose, as the title of the work suggests. We want to do all of this in an unsupervised way. So why is this interesting or important? Well, in the field of autonomous vehicle navigation, being able to detect and localize cars accurately is very important. So in order to do that, as you would imagine, we need to train deep learning models with a lot of data. And capturing millions and millions of data points can be very labor intensive. So having an unsupervised way of generating images given desired inputs, such as background and pose, is very cost efficient. So how do we propose to do this? Well, we basically take inspiration from conditional GANs. We encode three components. First one is pose. The second one is the model, or also we call it the appearance. And the last one is background. And each one of these encoders produces a latent vector that then we concatenate together to produce a single vector that we use to decode using a decoder or a generator in order to produce a target image. So two recent works are very relevant to what we've done and serve as our inspiration. The first is Jacob et al. In that work, they show that for generating humans in a given pose, they can basically encode target landmark positions and use that to condition the generator. Second work is by Men et al., and they not only show that they can use this with pose, but they can also use other style attributes, in their case, for generating different styles of clothing. So for our data set, we basically started looking out for existing ones. There are data sets out there, such as the Stanford CARS data set, that has upwards of 16,000 images. We quickly realized that they don't have a lot of images of the same car in different poses. So we resorted to collecting our own data set. So what we have here is a data set we collected of the same car at different locations and from different camera poses. So we have a total of 1,500 images of the car in the foreground and 736 images of the backgrounds. We took these images in two different locations. And we split this data set in a standard procedure in 80%, 10%, and 10% for trained validation and test. Finally, what we do for getting the binary poses, or the silhouettes as we call them, is basically we use mask-R-CNN and to extract instance segmentation, which then we threshold and get binary masks out. So here is the diagram of our proposed method with what I described before. So we have the images of the cars, images of the background, and the desired pose. All of these are going through their corresponding encoders, becoming the corresponding latent vectors, which we concatenate and pass through the generator. Now, the way we train this network is, the first component is we use a typical min-max loss for GAN. So that's one part, but also specifically for us, because we want to enforce pose and also background, we have a secondary loss component, which is reconstruction of basically the masked image that I'm going to describe in a second. So what we have is basically, we know the background image. This is provided as an input. We know the desired pose. We can basically mask out this image to get something like this. Also for the generated image, because we know the pose, we can mask out the car. Ideally, in an ideal situation, this is what it looks like. And then we can add this reconstruction loss, which is basically the L2 norm of these two tensors, to ensure or encourage the model to make sure that these two masked out images look similar. So I'm going to zoom out a little bit. This is basically, I described these parts, the encoders and the losses. Now for metrics, we use the standard IS, KID, and FID. In addition to those, we propose two new metrics, and they capture the fidelity of generation for the pose and appearance. For pose, we basically have IOU, which is intersection over the union of the input pose. This is a value we have or we provide. And also we can extract out of the generated image the binary mask in the same process that I explained before using mask-R-CNN. and we take the mean over the entire data set. So the range of this metric is between 0 and 1, and higher values mean that basically the model is doing a better job at putting the desired object, in this case the car, in the desired pose. And the second metric, we're calling it ISIM, which is the cosine similarity of the inception embeddings between the input car and also the generated image. So the intuition behind this metric is we want the output image to visually look similar to the input image if it is provided. And if you're familiar with cosine similarity, basically this is a value that ranges between -1 and 1. We take the mean across the entire data set, and higher values mean that basically the generated image looks visually similar to the input image. And it's more desirable in our case. Before I jump into the experiments, I want to quickly show you what the data set looks like. So this is an example of an input car. And this is us varying different poses. So this is what we want to generate. And these are examples, not cherry-picked, of the generated images. So you can immediately see that the model is actually doing a good job of generating in the desired pose, but the sharpness is lacking. And we'll see how this becomes a problem in the experiment section. So to quickly recap, the task is to generate cars given a set of inputs that could be pose, appearance, and background. Actually, the architecture is agnostic to exactly what kind of input you provide to it. You can provide any combination of these, including none, which just falls back to an unconditional gap. And the output, as we expect, is a generated car image. So the baseline we used, admittedly not a very strong baseline, but a good one to start with, was to basically compare with the randomly generated RGB images. The oracle we use to get an upper bound of what our architecture is capable of is to basically try to use an autoencoder to try to reconstruct the entire image, not just the mask part, and see how well we can do that. In terms of the protocols of the experiments I'm going to present, for all these experiments, we're training for 75,000 epochs. We're generating 256 by 256 images, and the Z vector dimensions are 256. So what we do is we evaluate the model every 500 epochs on the evaluation set, and we're reporting our metrics on the test set corresponding to the best evaluation results. And this is we use our notion of best is just the average of IOU and ISIM. So I'll be showing 3 experiments in this table. The first one is just providing pose. The second one is providing pose and car. And the last one is providing all 3 inputs. And basically what you can immediately see is compared to the baseline, all of these 3 experiments are beating the baseline. And also the second observation is only providing pose is the best, reaching the best results. So our observation, and we could see this anecdotally, is the more input types that we provide, the lower the sharpness. It's more difficult for GAN to consider all of those together and generate realistic images. So sharpness suffers, and as a consequence of that, also the inception score suffers. So you can see how this cascades, and basically as the sharpness falls, this also at some point starts to result in mask RCNN not being able to detect correctly the car silhouette. And this is why also IOU drops quite significantly in cases where we're providing both pose and car, or all 3 inputs altogether. So you can see that IOU score compared to the oracle, which is 0.4. If we only provide pose, we get 0.26, but we get close to 0 in these cases. And if you look at these images, it's not that they're really bad. It's just that the sharpness is not good enough for mask RCNN to be detecting these. And we have a similar observation for ISIM, where basically the best visual similarity you get with pose only, and adding more modalities or other inputs is not quite helpful. So in terms of future work, we hope to expand this work to data sets of more objects and more types of cars. And actually the architecture is agnostic to what kind of object you provide to it. We can simply swap out images of cars with images of humans or other objects and be able to generate given a desired pose.